enjoy the speed.
Hello, everyone. Just wanted to say thank you very much for coming. I hope the speed meetings went well, and I hope they were a lot of fun. That was the idea, to get you guys talking and sharing your experiences with each other. We're now in our next session with Grant from AquaTech. Grant is a professional engineer and a graduate of the University of Toronto's Chemical Engineering program. He's worked with AquaTech Sales and Marketing for 25 years, selling Lochinvar products. In his current role as agency sales manager, he oversees AquaTech's agency divisions in Ontario and BC. And over these 25 years, he's developed extensive knowledge of designing, implementing, and troubleshooting hydronic systems. So excited to learn about gas-fired hydronic boilers today, and I'll turn it over to you, Grant.
Great, thanks, Mark. Hi, everybody. Once again, my name is Grant Erickson there, and I get to talk to you guys today about gas-fired hydronic boilers. Aren't you guys lucky? Some of the stuff we're going to be talking about today, I'm going to be talking about the difference between condensing and non-condensing boilers. After we clarify that, I'm going to basically focus more in on condensing boilers because I think that's pretty much what everybody's putting in these days. I'm going to talk about the different types and styles of condensing boilers in the market. I'm going to talk about different piping options for those different styles of condensing boilers. Going to touch a bit about turn down and efficiency, and I'm going to finish off by talking about something a little bit near and dear to my heart these days, is water quality. So it does not sound exciting. So I'm going to start by talking about the difference between condensing and non-condensing boilers. What is the difference between the two? One condenses, one doesn't, I guess. The reality is they all condense. The only difference between the two is one is designed to handle condensing situations where the other is not. And one of the primary things you'll see with regards to the boiler is the material or the types of heat exchangers in them. Most condensing products will be made of something that can obviously handle condensate, like a stainless steel, cast aluminum, or sometimes they'll have like a dual or recuperative heat exchanger design. And most non-condensing products are obviously, they're using a material, usually a little bit less expensive, and something that can't handle condensate or doesn't need to handle condensate. And in most cases, what you're going to see out there is a copper tube, a steel tube boiler, or cast iron sectional type product. So I said every boiler is really a condensing boiler. Like condensation or condensing can happen in any type of boiler. Just some are more inclined or able to handle it better. So what happens with combustion? Well, stoichiometric combustion or perfect combustion, you're going to take a fuel source, and I'm going to talk about natural gas here, just because it's easiest. So you're going to take the natural gas, which is the CH4. You're going to combine it with oxygen from the air, O2. You're going to basically, get a source of ignition, a source of heat, something that gets that chemical reaction started. And ideally, what you're going to produce is water vapor and CO2. We know that there's no such thing as true, stoichiometric combustion. So you're going to get other stuff happening in there as well. But your main things that you're going to have are CO2 and H2O. And that water is in the form of a gas. And what you're doing with condensing boilers is you're getting below the dew point of where that water vapor will condense from a gas into a liquid. And when you do that, it releases energy. And that energy gets put back in your thermal balance, and that's how you get the higher efficiencies from a condensing boiler. Now, that dew point of natural gas will vary depending on the type of fuel you're using and the type of combustion that you have. So a fan-assisted type product with natural gas will have a dew point of 130 degrees. And that dew point of 130 degrees Fahrenheit is representative of your return water temperature. So anytime you operate above that number, and most manuals will say 140 because 140 sometimes can mean 130 in the field. Anytime you operate above that number, whether it's a condensing boiler or not, you're in non-condensing mode. And anytime you operate below that number, you're going to be in condensing mode. That water vapor is going to condense, turn to a liquid. As I said, it does vary depending on the fuel. So if you're using LP, that number becomes 122 degrees, and that's at 10% CO2. Of course, your type of combustion will vary how much CO2 you have in the stack. So an atmospheric boiler, some of us of a certain vintage can remember them. An atmospheric boiler won't have fans that control that fuel to air ratio. What they'll have is just a burner and Mother Nature, whatever the room provides for air. And a lot of times those will be less efficient combustion. So basically an atmospheric product in natural gas will have a percentage in the stack of roughly about 4.5% CO2. And that in turn comes to about 113 degrees Fahrenheit. So with an atmospheric product, you can actually have a lower return water temperature before you have to deal with condensation. As I said, it's all basically about that dew point, and I'm going to stick with fan-assisted combustion, natural gas from here on in. So that magic number is 130 degrees. So anytime you're operating above that, you're in non-condensing mode, and you're going to have a combustion efficiency of around 86, 87%. Anytime you operate below that, you're in condensing mode, and you're basically, you're going to potentially condense in there, and you're going to have a boiler and a stack that can handle that. You guys have probably heard of the term near condensing boiler, and a lot of those will have an efficiency of around 87%. They're non-condensing boilers. They need 130 degree return water temperature to it, but because that combustion efficiency is so efficient, that stack has the potential to have lower temperatures, especially when you modulate, and you'll generally need to have like a condensing rated stack for it. So as I said, condensing environment is obviously that one, like the rainforest. It's a very, very liquid environment, and a non-condensing environment will be like that desert, dry as dry can be. Now, if you took a condensing boiler, hopefully, and you put it into that condensing situation where you do want to apply it, that return water temperature, that cold water comes in, and usually it'll enter a section of the boiler away from the burner, usually because it's too hot near the burner, where most of the condensation will occur. So if you're looking at this one here, it would enter in the back there, and there'll be an area that's not exposed to that burner. And that's where you're going to get all that condensation to occur. Basically, all that, you're going to be pulling that heat out of the stack there. You're going to take that water vapor, is going to condense. It's going to go from a gas to a liquid. It's going to release a bunch of energy, and you're going to put that into your thermal balance. It then goes through, you get close to the burner, and you're not going to get a lot of condensation occurring where the burner is. It's just too hot. Then, of course, you go out to the system. If you took that same product and put it in a non-condensing mode, so maybe, this unit here, you got 150 degree return water temperature. That return water temperature is going to go into that area where condensation can occur, but you're not going to be condensing there. You still pull heat out of those flue products. You're just not going to pull enough to condense. Then, of course, you're going to go near the burner, and you're going to add more heat into the system there. As I said, it's all about changing state. That is where you're getting that extra efficiency out of it, right? So roughly 1 pound of water vapor is going to give you about 1,000 BTUs. So put that into gallons of condensate, which I think makes a lot more sense to all of us. 1 gallon of condensate is going to produce approximately 9,000 BTUs. And that's how you're going to get by basically grabbing, by condensing this water vapor, that's grabbing that extra energy. That's where you're getting above that 90% efficient range. Put this in perspective to you guys. If you have a 100,000 BTU boiler, for every 100,000 BTUs, you're going to get 1 gallon of condensate produced roughly every hour. So if you have a 600,000 BTU hour per boiler, you're going to get 6 gallons of condensate every hour. And of course, a 6 million, you're going to get up to 60 gallons of condensate produced every hour. So this 6 million BTU boiler will produce roughly around an extra 540,000 BTU per hour every hour, just from pulling this by changing state in the flue products there and turning that water vapor, water, the gaseous water there, into liquid. So the key difference between the two is one of them's able to operate below that dew point. The other one, it can operate below the dew point, but it's just not going to last you very long, right? The other thing you got to consider as well is your stack, almost more important than the boiler. If you're going to be operating in that condensing mode with a condensing boiler, you are going to need a stack that can handle condensate. And that's generally going to be stainless steel, CPVC, polypropylene. A lot of non-condensing boilers won't have those type of stacks. They'll use like a type B vent, which, is fine in non-condensing mode. But, if you actually do condense in there, it's going to rot out your stacks. So you guys have probably seen there's category ratings for boilers and stacks. And basically how it's divided up is whether it's in a condensing or a non-condensing stack, and whether it's a natural draft or a positive pressure. So a natural draft is basically, it's a negative draft system. So you're using the heat or the buoyancy of the flue products to create the velocity in that vent pipe in order to get those flue products outdoors. A positive pressure stack, you're using that fan that it controls the fuel to air ratio, but it is also going to push those flue products out. So you're going to need a pressurized type stack. So anytime you're in condensing mode, it'll be a category 2 or a category 4. You're going to need to have a stack that can handle condensate so it doesn't rot out. And when you're in non-condensing mode, it's going to be a category 1 or a category 3. And these type of stacks generally do not need to handle condensate because it's not designed to be in a condensing type environment. So as I said, you see most of them there are CPVC. Stainless steel, AL29 4C is probably the prime grade you see out there. That was really the first because very corrosion resistant. These days, you're starting to see some 316 stainless as well. And polypropylene works well in a condensing boiler as well. You know, type B vent is a very common one you see in a non-condensing type application. You know, there are other stacks as well, depending on whether you're positive pressure or negative. So as we said, you can condense in any boiler, any vent system. It's just whether it's designed to handle it. So if you're taking like a type B vent here, you know, it's an 85% efficient appliance and you operate it below that dew point, you're going to condense in that stack. That water vapor is basically going to condense to a liquid. It's going to be corrosive. It has a low pH, and it's going to end up rotting out that stack over time. Of course, you have stuff, you know, your flue products, you're venting them the outside for a reason because they're full of CO, CO2, stuff that you don't want to breathe in, and, you know, you can have safety issues here. So when you do condense, I think everybody's aware that condensate, it is water, but it's very acidic water. Generally, that pH is around 3.5 or so. It's very low, and that's going to rot things out. Like if you take a look, here's a picture of a copper tube boiler after being in a condensing environment. You know, it just basically starts rotting it out or rot out the burners. I don't want to see what the vent looked like here. So that's a little bit about condensing versus non-condensing. I think everybody these days is pretty much putting in condensing boilers. So I do want to focus on that a bit. When you're selecting a condensing boiler, there's a lot of different technologies out there these days. There's three main types of heat exchangers, and that's the prime thing you're really looking at here with a condensing product that you're going to consider. There's more than just this, but I think these are the prime ones out there. There's the dual heat exchanger, recuperative heat exchanger, which is kind of like two heat exchangers in one, kind of an economizer pulling that extra heat out of the stack. Cast aluminum is a popular choice, and of course there's stainless steel. I think most manufacturers have a stainless steel product out these days, and within stainless steel there's water tube and there's fire tube type heat exchangers. So the first one I want to look at is the dual heat exchanger or the recuperative heat exchanger design. So with this, you're going to have two heat exchangers. You're going to have a primary heat exchanger that does not condense, and in this picture here it's a copper tube heat exchanger, and you're going to have a secondary heat exchanger which is designed to operate in a condensing environment. And that's where all the condensation is going to occur. So with a product like this, you're going to have the return water is going to go into that secondary heat exchanger first. It's going to be exposed to those flue products, and it's going to basically, you know, it's going to have cold temperatures in it. So it's going to, you know, your flue products are going to condense there. That water vapor is going to turn to go from a gas to a liquid, and you're going to grab that latent heat here. And then this heat exchanger is usually like a stainless steel or some kind of heat exchanger that's able to handle that acidic environment. From there, it goes to the primary heat exchanger, which is a non-condensing heat exchanger. Now, a lot of times, if you're in a modulating type appliance, you won't be able to get that guarantee that you know, inlet water temperature to the primary is above 130 degrees. So a lot of these products will actually have a built-in bypass that will take some of that hot outlet water from the primary, recirculate it back in, so you do not condense in that primary environment. Cast aluminum is another product out there. It works well in a condensing situation. It's able to handle condensate. Usually with this type of appliance, what they've done here is they've kind of mimicked almost what a cast iron was. If you take a look here, there's all those heat transfer pins there. Flue products are at the top. The flue products are forced downwards. As it gets closer to the bottom, it's a counterflow type design. It's going to start raining in there, and it's going to start condensing, and that condensate will pool up at the bottom and you know, be piped out of the unit. I think there's stainless steel is probably the most common one these days. Most manufacturers, I believe, have a stainless steel product out there. There's two main types. There's water tube and fire tube. They have different properties, and you have to apply them a little bit different. And of course, there's a lot of different grades of stainless out there. I think 316L is a very popular grade, or 316 Ti. You see a lot of those. And that's what's called an austenitic grade of stainless steel. They tend to be high in nickel, which is good. There's also like 439 is popular out there. It's a ferritic grade. And then there's some people using various duplexes. A duplex is kind of a grade where they take a ferritic, austenitic, blend it together. But that's a whole other presentation. So let's talk about high mass and low mass stainless steel condensing boilers. When I'm talking about mass, I'm talking about water mass. Basically, a low mass boiler has less water in it. A high mass boiler has more water in it. So I said a low mass boiler is basically a boiler that has minimal water mass in it. They generally tend to be water tube type appliances where basically, the water's flowing through the tubes and it's surrounded by the flue products. Now, these type of appliances tend to have very specific flow requirements. I find, they might allow you to vary it a bit depending on the manufacturer and the type of heat exchanger. But for the most part, I find these type of appliances like static flow, and they generally have a very narrow range between the minimum and maximum flow through it. Some manufacturers just have a static flow that they want, give me this and nothing but. And as a result of that, when I'm dealing with low mass appliances, I always recommend primary, secondary piping for them. Now, high mass boiler is the opposite. It's a boiler with a lot of water into it. In the stainless steel condensing world, these tend to be fire tube design units. With a fire tube design, the flue products are in the tube, and it's surrounded by a large vat of water, big tank of water. And this does allow a little bit more flexibility when it comes to flow rates. They generally have, a much wider range of flow that they can operate in, and they tend to tolerate variations of variable flow much, much better. As a result of this, you tend to have more selection in your piping schematics. You can do the primary, secondary, which I personally know and love. But a lot of times you can do like a primary only system where you have VFDs, just system pumps pumping directly through it. So if you take a look here, this kind of shows the difference between low mass and high mass. If you have the same amount of BTUs on the bottom, you can take a look at the right, that low mass heat exchanger there. You can see if you slow down that flow too much, there's not a lot of water there to absorb the BTUs. And if that's too slow, what will happen is you'll flash the steam really quickly. And a water boiler that's not designed to be a steam boiler generally doesn't like that. It can cause all kinds of issues with your system and your boiler. You can also take a look here. It's a smaller tube. If you flow that too quickly, it's a small tube, you can erode that tube. That's why they generally have a much narrower flow rate or flow range requirements there. On the left here, you can see the high mass product. If you slow that flow down too much, or like quite a bit, there's a lot of water there to absorb those BTUs. You're not just going to flash the steam. And of course, if you speed it up, generally it's not a small tube. You're not going to erode the tubes. You're generally limited by the inlet and outlet connection diameter on that boiler to what your maximum flow rate is on it. So let's focus in a little bit more on low mass boilers to start. As I said, low mass boilers tend to be water tube type boilers where the flue products, the water's in the tubes. The burner is usually in the middle, like I'm showing here, and it's surrounded by the flue products there. Not a lot of water in there, so they heat up really, really quickly. And of course, I said I always recommend primary, secondary piping with these. I think this piping schematics, their situation's been around for a long time. I'm sure everybody's familiar with it, but let's do a review. Reviews are always good. The boiler loop is generally always referred to as the primary loop. Can be regional though. The system loop's usually referred to as a secondary loop, right? And I think you guys all know that really the secret to making all this work is these two closely spaced T's. See those two, and it doesn't have to be, it can be a low loss header or buffer tank. But those two T's basically, as a general rule of thumb, they say maximum 12 inches apart or 4 pipe diameters. And the reason why that's like that is because the pressure drop between the inlet and the outlet there, because they're so close together is negligible. And what that does is it accomplishes some hydraulic separation for you. So as that system pump turns on and off or ramps up and down, it won't affect the way the boiler pump operates on its curve. And as those boiler pumps turn on and off or potentially modulate, they won't affect the way the system pump operates on its curve. Each loop, the primary loop and the secondary loop, are hydraulically decoupled from each other. And that's the key, right? With these low mass boilers, they have that static or that very small flow range. You want to make sure the boiler's getting what it needs. Of course, you have the expansion tank. That's your point of no pressure change. So everybody knows that's the point in the system where that pressure will never ever change. And books have been written about it. You always want to pump away from that point of no pressure change there. So that's basically primary, secondary piping review in a nutshell. And it's very important with low mass boilers. Really, low mass boilers used to be there was all high mass boilers, steel tube, cast iron sectional, way back in the day. And what happened was how primary, secondary really came to be was way back when somebody started importing copper tube boilers. And, everything here, they'd have one pump on the system. They're used to putting in like a cast iron or something. They started putting these low mass boilers in. What they found is there's a lot of failures because that low mass product couldn't handle these high flow rates. So one of the pump manufacturers saw that this was a big issue and decided to tackle it. And what they did, I'm sure after quite a bit of a testing, was they realized that if they completed that secondary loop, that system loop, created those two T's there, I'm sure they messed around with how far apart they could be to achieve that hydraulic separation, put those in, put a pump that's designed to give the boiler exactly what it needs, it alleviated all these problems. So this is primary, secondary piping. The boiler basically is hydraulically separated. It gets the flow it needs, and the building is getting the flow it needs. And the genius of this for the pump manufacturer is now they're selling 2 pumps on this job instead of 1. So if you have multiple boilers, this is what your primary, secondary looks like. Generally, you have those 2 closely spaced T's. They're going to be done kind of like a manifold. So the inlet and outlet, maximum 12 inches or 4 pipe diameters apart. Your system loop, hydraulically decoupled from your boiler loop. If you take a look here, each boiler has their own pump size to give it exactly the flow rate it needs. The first one in is the last one out. The last one in is the first one out. So it's a reverse return situation in there. So it's self-balancing. Each boiler should get the exact same amount of flow because they're pumping through the exact same amount of piping. And of course, each one sees the same return water temperature. So they're all operating their maximum efficiency. It's not like in series where each unit would see a higher water temperature and be a little bit less efficient. Generally, if you pipe your multi-boiler low mass products like this, as long as you've sized your pipes and your pumps right, you shouldn't have any flow related issues with low mass appliances. So one of the things you got to watch though with primary, secondary piping is you always want to have more flow in the system loop or the secondary loop than you do in the boiler loop or the primary loop. Let's say you have a system like this. Let's say you have 3 zones here. We got a few boilers and we got a few VFDs, right? Because if something spins now, you have to put a VFD on it. Let's say you got, as these zones close, these air handlers shut down, you'll find like, okay, something's shutting off. The pressure's building up now, that zone's closed. So I'm going to start ramping that pump down. What can happen is you can get into a situation where you have more flow in the boiler loop than you do in the system loop. And what happens here is you're going to get some reverse flow. So a lot of that hot water you just heated, instead of all of it turning left, some of it here is going to turn right and go right back into that boiler plant. And you're going to start reheating that water you already reheated, right? This can basically get you into a situation where you're cycling and you can have some issues. So here, let's take a look here with some light math for you. Let's say you have 5 GPM here in this system loop and you have 10 GPM in your boiler loop. Well, your return is 5 GPM. 10 GPM goes into the boiler, 10 GPM comes out, 5 goes to the system. The other 5 reverses back and goes directly back into that boiler, right? So you're reheating that water you've already heated, less efficient. And what you can find is you can potentially get into a cycling situation. Say that building's cold, it's calling, I need heat. Well, the supply temperature set point, and let's say it's 180, whatever it is, 160, you might go out and you'd reach that and overshoot it. You're going to shut off because you're recirculating that water. Well, that room's still cold. It's going to basically draw that, within no time to say, hey, we're below set point, turn on, and kind of that on off, that cycling situation. And one thing you'll find, like any gas boiler does not want to cycle. Cycling is probably the hardest thing you can do for it and something you really want to avoid. So one of the solutions to that is putting a buffer tank in. With a buffer tank, you'll have a big amount of thermal mass there, and it's not going to be as prone to that short cycling, if you will, that you'll see in a standard primary, secondary situation. But there's other ways you can handle this as well too. What I like about buffer tanks is it adds mass to the system as well. You may or may not need it, but being a boiler guy, anytime I could promote longer run times to me is awesome. So let's take a look at high mass boilers now. So I said a high mass boiler, here's a heat exchanger for a high mass boiler. A high mass boiler, you're gonna have the flue products through the tube and you're gonna be surrounded by a larger mass of water. So if you take a look here, each of these tubes here will have dimples on it. And those dimples there are basically what it's doing is creating turbulence in that flue products. So you're maximizing your heat transfer that you're getting out of it. On the water side too, they'll try to create as much turbulence as you can, once again, to maximize heat transfer. Now, one of the things that low mass boilers do maybe better than high mass boilers is it's a much more turbulent environment. So if you're in a situation, let's say you have water quality issues in your building, and there's leaks, whatever it is, a low mass boiler would probably last longer than a high mass boiler, because those tend to be designed to handle domestic water as well. They're very turbulent in there, and scale comes out a solution where things are more stagnant. The more turbulent it is, the less likely that scale precipitates out. But anyways, that's kind of a tangent there. So they do try and make it very turbulent, or as turbulent as you can on that water side too, maximizing that heat transfer. Cast iron rods. Rods. Yeah, basically mass is how much water mass you have in there. So yeah, and anything that holds more water will add more mass for sure. It depends on the situation. A lot of low mass loops. I mean, it could be in a house, like let's say you have a boiler hooked up just to an air handler and you're back and forth there. That would be like a low mass loop. If you're in a house, probably okay, or in a big commercial building, that type of thing. So, but yeah, if it is very low mass, you find yourself cycling a lot, you do want to add mass buffer tank. There are some control solutions to that too, which I'll get into in a little bit. These new condensing boilers now have, the controls are just amazing, and most of them have ways to deal with it via controls. But at the end of the day, sometimes, yeah, if you don't have enough mass, you will need to add it. Anything that has more water, in my opinion, is good. So taking a look here, most of these fire tube designs, what they'll be is like a kind of a counterflow design as well. You'll find that as most condensing boilers will have it. They'll have the flue, basically the burners at the top. It's going to be the hottest portion of the heat exchanger there. You'll take a look there. The flue products go through the tubes. The tubes here have these dimples in there. That's not the only way to accomplish this, though. You're going to maximize your heat transfer coming out of there. Generally a counterflow design, so that cold water comes in the bottom first. Most of your condensation or condensing part is going to be occurring at the bottom portion of this heat exchanger. It's almost raining in that portion. It'll be collected and basically, piped to the outside there. As you get towards the top, you're not going to condense the closer you get to that burner. You're still putting a lot of heat into your thermal balance though. So another type of heat exchanger, here's a different type of design. This is a wave design where, you see this in some of the bigger commercial products. Where they take a big stainless steel tube, and those flue products, it'll be in this wave design where they're continually smashing against the walls because they're not just straight down, and that's basically creating turbulence once again to maximize your heat transfer. And there are other designs out there as well. So as I said, this type of high mass design allows for much more variation in flow rates. They generally have a much lower flow rate they can operate in, and a much higher they can go to. For an example, like a lot of them be between 10 and 110 GPM, and some of the residential, like commercial sizes. Some of the big commercial ones there go between like 30 and 350 or even 550 GPM, and they handle variations in flow quite well. So you can go to that same situation there where we have, VFDs on the system. You can just eliminate that primary loop and have it pumping directly through something like this. And that's another way that you can basically deal with that situation where you might get, less flow in the system loop than the boiler loop. But there's other ways as well. And this is a kind of a cool way here is variable primary, variable secondary piping. So with this, of course, you're going to have your VFDs on your system loop, but you can also have VFD pumps on the boiler loop. And with this, what's happening here is the boiler will drive this. So as that boiler ramps down, it's going to ramp its boiler primary pump down, keeping a constant delta T, and you're going to achieve some electrical savings by doing this. So take a look. A standard primary, secondary, something like this is modulating from 20 to 100% fire. In a standard situation with a static pump, as that boiler modulates down, the flow stays constant. So what happens? What changes? The delta T will change, right? So you might have sized that as a 20-degree delta T at 100% fire. But as you ramp down, that delta T will lessen all the way, in this case, down to 4 degrees Fahrenheit at 20 degrees modulation there. And basically, that's what's happening with a static pump here. But with a VFD pump, what'll happen is, there'll be an output from the boiler to that pump, and that'll basically drive it, right? So as that boiler ramps down, the delta T stays constant, so it ramps the flow down. As that flow ramps down, it's always going to keep it at that 20-degree temperature rise, and you're going to achieve a little bit of electrical savings here. But the other cool thing too is that the controls in most of these boilers can actually, it'll act as an anticipator here. So what it can do is most of these boilers these days can take an input from a VFD pump. So let's say you have a building here and I don't know, all of a sudden, it gets sunny. So part of that building, gets sunny, gets hot. Well, the zones close up, the VFD starts backing down. It'll send a signal to that boiler saying, hey, there's less load on the system. That doesn't affect the set point because the indoor-outdoor reset determines the set point. If it's 150 degrees, it's 150 degrees, but there's less load out there. So this is basically the boiler is going to do a couple things. One, it's going to alter its algorithm, its PID algorithm. So instead of maybe charging the set point, it approaches it much slower so you don't overshoot. The other thing it's going to do is it's going to know there's less load on the system. It's going to look at its system supply sensor, its inlet and its outlet temperature, and determine if it's in this recirculation mode or it's going to recirculate, and it'll start ramping that pump down to try and avoid that type of situation as well. So you always have less flow in that boiler loop than you do in the system loop. So these things are getting pretty advanced these days. I love a system done this way personally because I'm a boiler guy, so I want to be in control of everything. I find sometimes when other people are in control of my boiler, I tend to have more site visits than when we're in charge of what's going on there. So I like to control the pumps and everything. So to me, this is a happy system. I'll have a BMS or maybe something, or my onboard controls will do the indoor-outdoor reset. That determines the set point. So here, let's say we have a building management system. That says, hey, boiler, I need 150 degrees. Okay, I will lead lag my plant to give you 150 degrees. This is more of a macroscopic control. Then I'll have the VFD system pump saying, hey, it's there's less load on it. Okay, we'll alter our algorithm. We'll make sure we don't charge the set point. We'll also, take a look and we'll maybe ramp that VFD pump down if we're going to get into a situation where we have, too much flow in that boiler loop compared to the system loop. So with this, I like it because my boiler is in charge of everything. It's basically the BMS and everything's telling it what to do, but not how to do it. Most boilers have that other ability too. If you want the BMS or the system to tell it what to do and how to do it, that's possible too. But I like it this way because, boiler manufacturers spend a lot of time and effort and money to design algorithms for their controls so that they don't cycle and the boilers work properly. When you take that away, you're assuming whoever it is that's controlling it is going to do a better job than the boiler manufacturer of it. Sometimes they do, sometimes they don't. Or sometimes they do just as good a job, sometimes they don't. I want to talk a little bit about turn down as well for you guys in efficiency. It's funny, I always say, how many boiler plants are oversized out there? Well, the reality is for 99% of the year, every single one. Everything's oversized. They usually put in more than they need. But the reality is when you're designing, you're doing your heat loads, you're selecting that boiler, everybody's concerned about design days, the coldest days of the year, and matching that load so you have enough heat, which is extremely important. But how many days a year do you actually operate under those design day conditions? And I don't know, I've heard a lot of different opinions out there for 3 days, 5 days. The reality is it's not a lot. There's a graph here. It's actually from Chicago, but I think it's pretty relevant here in Canada. Some parts of Canada may be a little colder, some parts a little bit warmer, but Chicago gets pretty cold. So it's I think it applies. Here in Canada, quite often we're turning our boilers on in September. They're running all year until June, right? So if you take a look here, you turn it on in September, you're always at part load conditions until you hit those few coldest days of the year, whether they're in January and February, that you're operating those design day conditions that you've put all your effort into adhering to. Of course, then you go over that, it gets warmer, but we're still, most areas of Canada, we're running those boilers until June. So that's a good chunk of the year that we're doing that. And you can pick up a ton of efficiency by just, taking these part loads or these, most of that year into consideration. And that's really where turn down ratio comes in to help you out. Turn down ratio, turn down ratio is how low your boiler modulates down to. So you guys have heard a 5-to-1 turn down ratio. That modulates from 20% fire to 100% fire. A 10-to-1 turn down ratio boiler will modulate from 10% fire to 100% fire, and a 25-to-1 turn down ratio, and that's the biggest one out there that I'm aware of right now, will go from 4% fire all the way to 100% fire. And basically that'll match that load requirements of the building much, much better. I call them basically, it's almost like highway driving versus city driving. So high turn down ratio boiler will have less start-stop cycles. Any boiler and most machines will be most efficient at steady state operation. They don't want to start and stop. It's like a city, like your car. If you drive that same car in the city and you drive it on the highway, you're going to get much more fuel efficiency on the highway than you are starting and stopping in the city. It's the exact same thing with the boiler. Same with maintenance. If you take the car and you drive that only on the highway, you're going to need less maintenance than if you're driving that consistently in the city, having those start-stop cycles. It's the hardest thing a boiler can do, and it's very inefficient. And choosing a boiler with a higher turn-down ratio will get you that increased efficiency and will save you money on your labor bills, quite frankly. This is basically a 25-to-1 turn-down ratio boiler I'd put in a while back, and it's not an oddity. It's the norm, I find. This was actually an office building in Toronto, just off the 401 there. And after one heating season, I happened to drop by there and took a look at this, and I just snapped the picture because I thought it was cool. And most of them, once again, are like this. Most of them are actually 70% or higher, I find. So with this situation here, in this heating season, basically, this boiler operated at less than 25% modulation 86% of the time. So 86% of the heating season, this boiler had turned on, ramping up, ramping down, giving the system exactly what it needed without shutting off. Where, let's say you had a 5-to-1 turn down ratio boiler that only modulated from 20, or we'll call it 4-to-1, from 25 to 100% fire. Well, what would happen? Well, if that system needed one boiler at 10%, well, this 25-to-1 turn down ratio, or the 5-to-1 turn down ratio boiler would turn on. It'd have more BTUs than the system needed. So it would overshoot that set point temperature because it only needs X amount of BTUs and we're giving it a lot more. Overshoot it, shut off on supply set point, but the room's still cold, still calling. Let that cool down a bit. On, off, right? You're going to be less efficient and you're going to basically need maintenance faster. I don't care what that piece of literature says, the actual efficiency of the boiler is. It could be 3 points higher in efficiency. This one here will have a better overall boiler plant efficiency. So let's take a look at a building. So let's say we have a commercial building here. We have a 6 million BTU load. Well, let's say we size it to load. We have 3 boilers sized to load. So usually I like to do, if one goes down, you can have 60, 65, 66% redundancy, which we're achieving here. And we put in 3 25-to-1 turn down ratio boilers. Well, what's happening here? That gives our overall boiler plant a 75-to-1 turn down ratio. So that means we're modulating this plant from the lowest rate on this boiler would be 80,000 MBH, all the way up to, all of them together at 6 million. So basically, you'd be matching that load from 1.3% of the system load, all the way from that warmest day of the year, all the way to that coldest day of the year. And you're going to be significantly more efficient than, let's say, you put in 3 5-to-1 turn down ratio boilers. Well, that will give you an overall boiler plant turn down ratio of 15-to-1. You'd have significantly more start-stop cycles. You'd be less efficient, and you're going to need maintenance faster. So definitely look at turn down ratio if you have a customer that's, looking as concerned about efficiency and is concerned about maintenance. Now, as I said, a lot of these boilers, I like talking, controls as well with these. They got very advanced controls in there, and a lot of people just put in the boiler, kind of put it on, maybe set the set point or the indoor or outdoor reset and leave it at that. There's so much more to most of these boiler controls these days. Most of them have built-in sequencers for multiple units. The most prominent control strategy out there is that lead lag. First one goes on, when you need the second one, once that's past its 100% firing range, it'll turn that second boiler on and so on. They'll usually rotate that lead boiler 24 hours, or a lot of them are actually programmable how you do that. So that's one option out there. Most manufacturers now have another option too, called efficiency optimization. So with efficiency optimization, what the theory is, like, any of these boilers are going to be most efficient at their lowest rate of fire, because you're going to have more heat transfer area per BTU provided. So with this type of control scenario, instead of one boiler on at 100% fire, you'll have 3 boilers on at 33% fire, giving you a little bit more efficiency out of it. My personal opinion, I like lead lag, because I found that maintenance is usually more expensive than the gas costs. Because here, you have 3 boilers on as opposed to 1 boiler on, so you're going to have more wear and tear on it. That being said, with some of these, the increase in price of gas for all the additional carbon taxes, maybe that'll change soon. Another thing you want to look at is the indirects, or if you're doing domestic with it as well. A lot of these can handle domestic through an indirect tank, which is basically a tank with a coil in it. There's two different options. You can do it as a zone, which is off your secondary or your system loop. And a lot of them will have it doing it off a priority. Now, for a house, you might, or a home residential situation, you're generally, or you might be in a situation where your domestic load might be higher than, you know, what your heating load is for that house, right? So in that case, you're generally going to size your boiler for your domestic load, and you're going to hope that your modulation will handle the rest, so you don't get into cycling or overshooting issues with your house, with your heating load. Although it's not always like that. You can be in a situation here like this. Maybe it's an office building, you know, light commercial situation where your heating load is significantly larger than your domestic load. Well, you can get into a cycling situation here as well. Let's say this is a 2 million BTU per hour boiler. It's handling the building, but they're just doing hand washing, right? It's just an office building. There's not a big domestic load. So let's say this indirect is sized so that basically it'll take about 500,000 BTUs, that coil well, right? So what's going to happen on a call for domestic? Well, this boiler, I said, as smart as they are with these controls, they don't know what they're hooked up to. So this boiler is going to basically get a call for domestic. All right, it's going to turn that on, and what's going to happen here is that it's going to, you know, it's going to be cold in there. So it's going to say, oh man, you know, my set point's 180 degrees because I want to ramp that domestic tank up as hot, you know, as fast as I can. So it's going to turn on. It's going to see it's far away from set point. It's going to slam 2 million BTUs into there. Well, what's happening? The coil's only taken 500,000 out. So it's going to go, and it'll overshoot because we're, you know, it'll go 180, 185, whatever you have it, and then it'll just shut itself down on temperature. Well, tank's still cold. It'll wait till that cools off a bit, strip that heat out, and say, turn on again. It'll turn on, off, on, off. And once you get into that cycling situation, which you want to avoid. A lot of times what these boilers will have built in is you can actually program, you know, a modulation rate or how many BTUs when it goes into domestic mode. So if you do that, you can program in like, hey, boiler, when there's a call for domestic off the primary, only ramp up to X amount of fire, or only put in 500,000 MBH. So it'll say, okay, domestic mode, boom, I'm ramping up. My maximum is 500,000. I'm not overshooting. I'm going to get a nice long runtime. I'm going to be more efficient, and I'm going to require less maintenance. Another cool thing that these guys have in here is sometimes you can control how aggressive, not even just the boiler itself or the boiler plant will operate when using the onboard controls. So let's say you have a situation like this. Maybe you have a building here that has future expansion. So what do we got? When the future expansion goes here, we have 2.5 million BTUs here. Well, we're buying this boiler today. So we put in a 2.5 million BTU per hour boiler, but, you know, 1.5 million isn't running. So what'll happen? You know, turn it on in the morning. It's all right. We got to heat this building up. Well, okay, let's say the set point's 160 degrees and, you know, we're down at like 80 or whatever, right? It's cold. We need a lot of BTUs. We've got to ramp up. Okay. We're going to turn on, once again, this boiler. It's smart, but it's not smart enough to know that it has less load hooked up to it. So it's going to say, oh, I'm far away from set point. I need to be up to 160. I better ramp up and put my full 2.5 million BTUs in right now. Well, it's going up, it's slamming 2.5 in, and all of a sudden it's operating so quickly, only 1 million's coming out, that once again, it overshoots that set point. Well, it has to wait until, you know, it cools down a bit. The room's still cold, it's still calling, on, off, on, off. Once again, you get into that cycling situation. So a lot of boilers now have something called a ramp delay feature. With ramp delay is you control how fast you get up to 100% fire. And you can usually do it in increments, like 20% increments. So in this situation, you could say, all right, put on the ramp delay, but take 15 minutes, 20 minutes. I like slow, the slower the better, to get up to set point. So it'll say, okay, I've turned on, it's cold in the morning. I'm going to go ignite and I'll go down to low fire, in this case 4%. I'm going to slowly modulate up. I'm going to take 15 minutes before I get to full fire. And it'll slowly get. What'll happen is it'll go up and it'll find and just maintain that set point and probably stop its modulation, never ever hit full fire, never get into that cycling type situation. So that's a way controls can handle like a lower mass, or, you know, in this case, like where the BTUs don't match up. You have way more BTUs than what you're taking, you know, putting into the system than what you're putting out. So it is worth, when you're looking at these manuals, don't just put it in, set the set point and walk away. There's so much more these boilers can do. Most situations, you don't necessarily have to do some of this stuff, but be conscious of it, because if you do need it, it's nice to know that they're there, you know, as opposed to maybe Buffer tanks are great. I sell buffer tanks. I love them. But, maybe you can solve your problem with controls as opposed to just going directly to adding mass to that system. And save yourself and your customer a bit of money. I'm going to finish up here by talking a little bit about water quality. Water quality is an issue. Water quality is very, very important. And, what I find being a boiler guy is that if there's issues with water quality, it shows up quite often in the boiler. So I always like talking about it here. And it's very important, putting proper quality water in there will protect the investment, your customer's investment in their heating system there. And whether it's new construction or retrofit, you always got to be conscious of water quality. Retrofit especially, because I don't know why. There's magnetite, there's a whole bunch of crap in these pipes. It's operated fine through the years. It hasn't taken down the existing boiler there. But as soon as you replace that boiler, you rattle the pipes or something happens, all the crap just comes out of the pipe. It always does. So be conscious of it and deal with it. So, 6 months later, there's not a non-warrantable failure happening there. So untreated water is bad, especially if you have leaks or anything like that. Because with untreated water, you're taking on new fresh water that brings in more scale into that solution. As I said, when you heat water, scale precipitates out. When there's a heat source there, it adheres to it. It forms a hard brick-like substance, which one is a fantastic insulator. So you're less and less efficient every day. And two, it's expanding and tracting at a different rate. It's causing uneven heat transfer in your heat exchanger, and that heat exchanger is going to fail much, much quicker. So you definitely want to avoid that. So you always want to make sure you have quality water putting in there. Prior to your initial fill, I would say isolate that heating appliance and flush your system out. Clean the system with a approved pre-conditioning cleaner to remove any debris. Clean all your water filtering devices. Any of the crap that somehow, is in there can get dislodged, and flush cleaning solution out the entire system and refill it. Very important, Whether you want to do it with everything, your initial fill, you want to make sure your makeup water is treated and you have good water coming into it, not just city water coming in, because if there's a leak, you're going to potentially lime it up. And some of the main additives you're looking at with hydronic system, I find, is hardness, which generally consists of calcium, magnesium. But there's also total dissolved solids. That's everything that's dissolved in there within a certain size range. Your pH is important. Chlorides as well, especially with a stainless steel product, because chlorine is the one thing that really kills stainless steel, whether it's in the water or actually also in the air. I've seen where some people think it's a great idea to put their pool chemicals right next to the boiler. Well, that stuff gets in the air. If you're drawing combustion air from the room, that goes right in. As it gets in, it mixes with the condensate and the condensing boiler, and you can basically rot out that heat exchanger. And of course, sediment, that's going to build up in your boiler heat exchanger and once again cause a non-warrantable failure. I recommend monitoring your wake-up water because sometimes there's leaks in the system. You don't know. If you find that you should have less than 5% of your total system volume per year in makeup water. If you have more than that, something's leaking. If it's untreated, you have more scale coming into your hydronic system that's going to precipitate out. And always repair your leaks. I recommend only conditioned water is added. So, put something to condition it in, or have one of those tanks that basically like a glycol feed tank or whatever with water. So, if it drains, it'll sound an alarm. It'll let you know you got a leak somewhere in your system. Now, if you're using glycol or antifreeze, always remember that does affect flow rates. So, and your duration. So basically, the more you put in, you're going to end up derating your boiler. So like a 50% glycol solution will derate your boiler by about 11.5%. So if you're not comfortable with that deration, you can increase your flow rate to overcome that. So you'd have to increase your flow rate by about 13% in order just to overcome that potential deration that could occur from it. Most boiler manufacturers, gas boiler manufacturers, will require levels like this: hardness between 5 and 12 grains. Total dissolved solids generally below 350 ppm, pH between 6.5, 8.5, and chlorides, of course, you want below 150. Now, electric boilers are different. Most electric boiler manufacturers require significantly less dissolved solids and less hardness in the water. Generally, there are electrodes in a little tank of water, so they can be prone to lime up. So always check your boiler's water quality requirements. I always recommend filtration devices. always, because if there's any crap in that system, it's a retrofit. You stir it up, it will end up in that boiler. So you want to prevent that from happening, because your brand new boiler could be a repurchase there in within months. Put in Y strainers. I recommend them. Always when you're put in quality water originally, I recommend demineralized water. Don't put in RO or distilled water, because those waters tend to be like raw water. They're very aggressive. They want stuff. So basically, they're going to be pulling out of your system. They're going to be, pulling out different stuff in your system to put it into the solution, because it has nothing in it. So go with the demineralized. Said chlorides, always be conscious of them. And personally, I always recommend like Y strainers and dirt magnetic separators, because more and more magnetite is a problem there. It can cause issues with the boiler, especially if you're in like a higher mass boiler where it's less turbulent in there. Sometimes the sediment can go in. It'll basically go get lodged into a corner or something by the fire tube, create like a galvanic cell, and start corroding that heat exchanger. And of course, your ECM pumps, it can cause problems with as well. So that was a lot of content I jammed into a small enough time period there. Not sure if anybody has any questions now, or.
Yeah, we can monitor some questions if there's anything. Yeah, you did go through quite a bit there. One thing is I'll ask you: is there a way that people can reach you, or give a little plug for AquaTech there as well?
Yeah, so basically, AquaTech's been in business since 1980. We are basically the Canadian national distributors for lock and bar products, except for Quebec. So we do not handle the province of Quebec, but we handle all the rest of Canada. And what that means is we import the product and we distribute across the country. Our head office is in Burlington, Ontario. So we operate out of a 75,000 square foot warehouse office space there. And we house, products for Canada and parts there. We do have a 5,000 square foot warehouse office space in British Columbia as well, where we do our own sales in most of the Ontario market and BC market. But the rest of Canada, we do have reps agencies that work with us and handle the sales there. We've been around for a while. We're all boiler guys, and we try and hire a lot of technical people here, whether engineers, gas fitters, that type of thing, plumbers, people that have been in the industry and hung out in boiler rooms, basically, to help you out if you have any problems. Perfect.
Yeah, I can tell you there's a lot of great people at AquaTech. So definitely. Any questions at all? You can put in the chat. If not, you can take a little break before our next session. I'm not sure if anything's coming through, but no, I appreciate it very much. It was. I learned a lot because, I don't know as much, probably nearly as much as as the people on the thing, but it was great. So I appreciate it very much, Grant. It was really great. So
awesome.
Thanks for joining us today.
Thanks for the time.
Yeah. Our next session, just for everybody, is with Michael Ridler. It's going to be a little bit different because it's there's no PowerPoint in this one. He's in a live lab, so it's going to be all live, so it'll be interesting to see how he navigates that. So we'll see, but please join us in that one. But thanks again, Grant. It was a great presentation. Appreciate you joining us.
Cheers.
All right. Take care, everyone. See you shortly.